Hey there, in this video we're looking at C++ Interlude 4 in the Walls and Mirrors Data Structures course. And this one's about safe memory management using smart pointers. For my students at CUNY Kingsborough, this will be a new feature of C++. And up until this point in our curriculum, we have been using what's now called raw pointers. If you're declaring a pointer like int star, we now refer to that as a raw pointer. And that matches what's actually happening in the CPU to access memory, but it does have pretty large risks that you might accidentally cause a memory leak or a dangling pointer or corrupted memory or something like that. So nowadays in modern C++, it has an add-on set of features called smart pointers to help hopefully protect you from those kinds of issues. A lot of people nowadays working professionally would recommend that you just not use raw pointers like we've done until now and really restrict yourself to only these smart pointers, or technically they're supposed to be called managed pointers. So a really important, relatively new feature in the C++ language that you should definitely know about. So let's think about how we've been using raw pointers up until now and what one of the problems that we've been unable to correct at this point. So usually what we're going to be doing is we're going to be dynamically allocating memory in the free store, what you normally call the heap, by using the C++ new operator. And of course, if you're using that, you must use a pointer because you don't know in advance where that memory is going to be laid out in the heap in the free store. So the operating system has to tell you, we found this block of memory at this particular address, and then you have to store that in a pointer, of course, is what it's for, to keep track of it and use it and clean it up at the end. Now, you're storing that reference to the object in the pointer variable. You're using that pointer variable to access the object, like we're saying. And then one thing you can do, and sometimes you need to, is you can copy that reference to another pointer variable. So then you'll be in a situation where you have two or more pointers that are actually referring you to the single one object in the free store. People frequently refer to that as an alias. An alias is when you've got multiple pointers to the same object. And sometimes you'll have separate parts of your system that need to keep track of a particular object. And that's kind of an obvious thing that has to happen once in a while. Maybe you've got separate functions, you've got separate container classes that need to keep track of that. Is fairly common. Okay, so you've got these aliases, and then of course at some point to clean it up properly, you're supposed to use the delete operator on a pointer, deliver the address of the memory block to delete, and the operating system marks it for recycling, marks it for reuse by maybe other programs or something like that. And we here have recommended that assuming you're using a private data member for that pointer in a class to keep track of it, that then you set that pointer to null pointer just to remind yourself basically that that pointer is no longer pointing to a legitimate valid object on the free store. Okay, so that's fine, but it's only fine for one pointer because remember, you might have other aliases, you might have other pointers in the system holding that address to that object that you dynamically allocated, and they don't have any way of knowing that the object was deleted and reused by some other system. So you might have to, in order to solve that, you have to somehow keep track of all the aliases, keep track of all the pointers that were ever directed at that particular object, and clean them up properly, assign null pointer to them and don't use them again. Otherwise, you're going to have those canonical, enormous catastrophes of dangling pointers and memory leaks and program crashes and memory that you can't access anymore while your program's running, and all that stuff is going to happen. So that is the problem of aliases, multiple pointers that we still have to come up with some kind of clever way of fixing. So let me just make a little bit of an aside. You might possibly ask at this point, why have we spent time studying raw pointers in C++ in the first place when a lot of people would recommend that in practice you maybe shouldn't ever use them anymore? And you know what? the creator of C++, Mr. Bjorn Strustrup, would actually say that, would actually take a little bit of offense that anybody is teaching in college courses raw pointers. But our perspective here and our focus here is kind of a deep understanding of what goes into programs and what goes into software. So we want to make sure that you understand how a computer really works, and the registers on the CPU that are managing memory, they just hold numerical addresses. That's it. They don't know about smart pointers that we're going to learn about here. We want to make sure that you can interface with assembly language in your computer architecture course when you need to, because assembly language only has basic raw pointers. It doesn't know about anything else. We want to make sure that you can understand the security problems that we have nowadays in software because of pointers and dynamic memory allocation problems. So if you're going to be someone that helps us solve these problems, you need to know where the problems come from. So I personally think that there's a lot of important reasons why we need to start with what, to my mind, is the real deal, the real pointers, and now we can add some of these more recent features to hopefully protect us a little bit. So that's kind of the path that we've been on for a while. Okay, so let's think about how some other languages deal with this. So other languages in the modern world nowadays, like Java or Python, they don't allow you to directly reference objects by pointers. They effectively hide the pointers from the end programmer. So again, systems and CPUs need to have pointers, but these languages basically hide them from you and don't let you directly interact with pointers. So what they do instead is they have an intermediary object that you refer to, and the system automatically handles the references and the pointers behind the scenes to hopefully make it not possible that you accidentally screw them up in one of these ways. So one thing that you could do specifically on the alias issue is that you could have an object that knows about all these references and keeps account of how many references or pointers do we have out in the world referencing this one object. So that's kind of what we're going to do here. That's referred to as the reference count, is basically the strategy that is used in C++ specifically. Other languages might use slightly different strategies possibly. And then any one of these languages, however you're going to do it, wind up being able to detect when an object doesn't have any live references anymore, when all the pointers or references or whatever you want to call them have gone out of scope, they can detect that, and then the system automatically deletes the object. So languages like this, like Java, don't have a delete operator. They have a new operator for when you need to make a new object on the free store, but there is no delete operator in the Java language because Java will just do that for you automatically. That's called garbage collection in a language called Java. And for what it's worth, the Java garbage collector kind of has a mind of its own. Is occasionally it's kind of like, I don't know, janitorial services. It comes through, checks the current memory, sees if there's objects that lack references, and those ones get cleared out at that time. Now the problem with that, I guess as a C++ programmer, the problem with that is we don't have any control over when Java decides to do that. So the garbage collector could kick in, I don't know, soon. It could come in later. You might have objects you're not using just hang out in memory for a while, using memory that you can't get back for a little while. The garbage collector might kick in at kind of a vulnerable moment. If you have like a video game possibly, I think this actually does happen in Minecraft, to my knowledge. You have kind of an important moment, and all of a sudden that's when the garbage collector kicks in, and the whole system slows to a crawl while Java goes through the memory system and looks for things that it can clean up. So that, entirely letting the system take control of it is not the C++ philosophy. The C++ philosophy is to always have, if you need it, complete control over the system and try to make things as fast and efficient as you possibly can when you need it. So the garbage collector, the automatic garbage collector, is not the approach that C++ took. Let's see what the approach is. So C++ does now support what's called smart pointers. Technically, in the formal documentation, they're called managed pointers, but the community kind of fell into the habit of calling them smart pointers, so it's probably what you're going to hear me say most of the time. So you get the same functionality as raw pointers. So you can keep track of an object in memory, you can conveniently, efficiently pass addresses between functions without copying the objects. You can dynamically allocate things on the free store and use them to track that. So all the labor, all the work that you need pointers to do, you get from these smart pointers. And in addition, they also provide automatic memory management. So they are going to keep track of a count of how many references there are in the system. And then when that count goes down to the 0, at that moment, the smart pointer is going to take charge of deleting, recycling that block of memory. So when you declare a smart pointer, if you declare it locally in a function, right, the smart pointer will be an object on the stack like normal, or you could dynamically allocate the smart pointer itself in the free store, although that's kind of unusual because you normally use the free store for big things. Smart pointers are mostly just an address and a little bit more data. So the smart pointer is now, you have a reference to the smart pointer, which is itself an object, kind of like a middleman between you and the actual object in the free store. So when you have declared one of these smart pointer objects, it has a real pointer, for what it's worth, over the actual object. And when you've got that set up, we've referred to that as having the object managed by one of these smart pointers. Okay, now in current C++, and C++ is always evolving for what it's worth, but currently in C++ it has 3 types of these smart pointers. So specifically 3 object types that you could choose from when you are declaring a smart pointer. So we'll go through them in this order here. So number 1, there's unique pointer, which prohibits any other pointer from referencing the same object. You get one pointer, you cannot make an alias. You cannot make an alias with a unique pointer. So that's one way of solving the problem. If you use a unique pointer, it just prohibits the whole alias problem. And then you don't have dangling pointers that way, at least. So that's kind of a wrecking ball approach to the issue. And I mean, in certain circumstances, that's all you need. It's very simple. But there are situations where you do need more than one pointer. In fact, we've seen them before if you look carefully in this course. So if there is an object that you do need multiple pointers to, the type for that is a shared pointer. Shared pointer, specifically an object to manage how many references do you actually have. So that will safely permit shared ownership of the object in question. And again, if you have 1, 2, 3 references to it, okay, fine. And then as they go out of scope, I have 3, 2, 1, 0 references. The shared pointer sees that, knows when that count goes to 0, and then it automatically deletes the object off the free store. The weak pointer is a third option, is if assuming that I have a shared pointer taking ownership of the object, so to speak, you can make another alias call a weak pointer, which is a reference to an object that's already managed but does not have ownership. So what you're saying with a weak pointer is, I promise I definitely am not going to use the weak pointer to delete the object. That's not the question. I am just getting a copy of this address. I'm referring to it that way. We know that there's another pointer, specifically a shared pointer, that's actually responsible for deleting the object when you run out of references, but I can at least use this temporarily to refer to this object here. So a couple of things to be clear about. Number 1, when we say ownership, we mean that's the pointer that's responsible for deleting the object when we're done with it. So unique pointers and shared pointers automatically take ownership of it. Weak pointers don't do that. And the other thing is that when you're using smart pointers, you'll never use delete. Just like Java doesn't have a delete operator, you don't need to use delete. You don't need to remember that part, because the smart pointer itself will automatically take care of it when it detects that there's no references in use in the system anymore. So that's how that's going to work. Now, a couple tiny little side points. At CUNY Kingsborough, if you look in the right place of our prior textbook, of our introductory C++ textbook by Gaddis, that does, in one place, it briefly introduces the unique pointers. Just that one, just to keep it simple. It doesn't talk about these other ones, for what it's worth. And the other thing that I would say is that if you're using much older C++, again, as it evolves over time, there used to be, before any of this stuff, there used to be a type called an auto pointer that I think came out in C++ 98. That was deprecated in 2011, which means it's recommended you not use it anymore. And then as of 2017, it's been officially removed from the language entirely. So if you were a long-time C++ programmer, you might have been using auto pointers, and it had some weaknesses. You couldn't use it with STL containers that we'll talk about later. So if you ever used that in the past, nowadays it's unique pointer that does that job but better. Okay, so before we dig into the specifics of those three smart pointer types, let's talk about another keyword in C++ that's going to be new for my students, called auto. And the reason why this will start being of interest to us now is that our type declarations, when we start declaring these smart pointers, the type declarations might become kind of long and unwieldy on the screen. For example, the smart pointers are templates. They're template functions. So you make one of these smart pointers and you'll have angle brackets and you have to specify what kind of thing you're pointing to. Well, maybe it's like a plain box or something like that. Well, remember, plain box was templated. So when you specify a type plain box, that has to have angle brackets. And you have to specify what type of thing is in the box in those angle brackets. And I don't know, what are you storing? Maybe you're storing a vector. Well, a vector is a template. And when you specify that, you have to say vector angle brackets like I'm holding floats or something. So you might have this templates and templates and templates and templates declaration that starts to get a little bit hard to look at, frankly. So one option is that there's a keyword auto in C++ now that when you declare a variable of some type and initialize it. So it's like you're doing something like int val equals number, or maybe the return of a function. You can replace the type with auto and say, hey, compiler, just figure out the type for me from the initializer, is what that does. So just auto. So to be clear, auto is not a type itself. It's not changing how anything's stored, but all it's doing is in the code that you write, it's going to look at the right-hand side of the equal sign on the initializer, look at that type, and then come back and say, well, I guess this variable we're making must be that same type. So auto automatically figure out the type of a newly declared variable. And the specifics there is that auto in C++ 11 tells the compiler to determine the type of a variable from its initializer. And then in C++ 14, they added the ability of that to use that like it's the return type from a function. And then the compiler will look all the way down at the bottom of your function, see what kind of thing are you trying to return, come back up and say, well, that must be the return type from this function. Okay, so kind of adding things you can do with it. So assuming you're working with C++ 14 or later, you can use that to shorten the declaration of a variable, and you can also use it to shorten the prototype for a function that you've implemented. Now, to be clear, it's not an actual data type. You cannot use it as a type that you're storing something in, and you cannot use it as the parameter into a function or a method. That has to be a specific explicit thing because there's no way that it can figure out, assuming that you haven't got function calls in the code that it's looking at. Usually those things are separate modules. So we're going to be seeing some examples of auto on the following slides as we go through our smart pointers. Let me just talk a little bit about pros and cons. You know, I use auto sometimes. I don't use auto all the time. So some benefits you get from using it is it does make your code shorter. Brevity is good. We like that. It does sync up with the don't repeat yourself principle. So, you know, if I'm dynamically allocating memory, previously, I've been doing something like, I don't know, int star for a raw pointer. So int star my pointer equals new int. And you notice that I wrote int twice on that line. So you might start to look at that and go, hey, wait a minute, you're repeating yourself. And particularly when they're longer templated types that you're dealing with, it's like, why am I writing that type twice on the same line? So I get that. Auto said, why am I doing that? Let the computer do that. And that's exactly what auto does. Just write the type once on the right, and then auto fills it in on the left for you automatically. It also handles if you change the return type from a function. So let's say, one day I had, get the temperature and it returns an int. And then there was some function that, calls that function and stores it in a variable. So obviously that variable has to be an int. But then some later day, I want more precision and I change the return value to a float so I've got decimals. Well, then the variable that I'm storing the result in also has to get turned into a float. But if I've made it auto, the compiler will take care of that automatically for me. So that's kind of nice. So there's a bunch of advantages that you will see auto in a lot of code nowadays. Not everything's positive. A negative that I've run into is it starts to become a little bit hazy what types you're actually dealing with. So in slightly more complicated code that I was working on recently, I was writing auto variable equals return from some function. And then I looked at it and was like, I have no idea what type that is now because I'm not seeing immediately what type the function's returning. And auto is sitting here for the type of my variable. And now I'm like, I guess this will work. I hope I'm using the variable right in the code that I'm writing afterwards. And I start to just be a little bit less confident that I really know what's happening here because I'm not seeing the type on screen anywhere. So, maybe I'm an old fogey and I just need to get used to that. But I think there's some benefits to actually seeing the explicit type to communicate what is this code about, frankly. So, feel free to start using auto. Use it judiciously. Use it when you are clearly shortening something that's repeated, you're repeating types on. But I wouldn't just turn all of my declarations all into auto. I feel like that's probably not clearly readable code at that point. But maybe my opinions and maybe your opinions will evolve on that. Now, the other thing that I'll point out here is that I'm pointing to like specific features in particular flavors of C++. And if we haven't said it before, when we say C++ 11, we're talking about the standard that was written in 2011. So usually now the standards come out 1 year, and it usually takes several years before the compiler programmers get around to updating the compiler for C++ that has all these new features that come out every couple of years. And then it takes a couple more years or something to release those new compilers, to get into the IDE systems like the dev C++ package, and then finally get to actual people. So the standards are numbered at some point when the document gets written, and then it might be some number of years before you can really rely on it being available and used in a whole bunch of different company systems, stuff like that. I will say historically, there was a period from 1998 to 2011 where C++ was very stable and it wasn't changing much at all. And then there was this kind of sea change in 2011 where the maintainers of C++ really dedicated themselves to updating, to modernizing, to bringing in new features into the language. So there was a big release in 2011 that really changed a lot of how people use C++. And you've probably seen us refer to C++ 11 sometimes before. We'll continue to do that. Currently, as I record this video, I have my classes, students in my classes, I request that they are coding to the C++ 11 standard because I think it's the most widespread one now that we can rely on everywhere. And the C++ committee now has a plan, if I'm up to date on it, whereby they release a new standard every 3 years. So there was one in 2011, there's one in 2014, 2017, and they're trying to continue on that cadence of staying up to date with modern programming practices and adding more features. So C++ has been changing rapidly in recent years. It seems like it will continue to do that. Whereas when I was a lot younger, there was C++, and we could just kind of take that for granted for 15, almost 20 years at that point. And now there's kind of a cutting edge to it that they try to maintain. Okay, so back to smart pointers. Remember, 3 types of smart pointers that are in our toolbox now: unique pointers, shared pointers, and weak pointers. So let's deal with each of those. Okay, so unique pointers, probably the simplest one to get started with, so we'll cover that. It was technically in our textbook last semester, if you look in the last place. So to be clear, a unique pointer has solitary ownership of its managed object, right? It's the only thing that's allowed to reference it. That just wipes off the table the issue of aliases. It's just not possible at that point. You can transfer the ownership to another single unique pointer. So there's a function in the C++ standard library called move that specifically says, I've got ownership in this unique pointer, but I'm going to move it over to this other unique pointer. And now that's the one and only thing that can refer to this object. So you can move it around, but at all times, there's only one single pointer, one unique pointer referring to the object in the free store. You cannot just assign it. So if I have unique pointer number 1 and unique pointer number 2, and I try to do pointer number 1 equals pointer number 2, compiler error. Won't permit that, right? The only thing you can do is use move, because once you give it to another pointer, this pointer doesn't have it anymore. So that's how that works. So a couple of different ways when you want to do this that you can declare a unique pointer. Again, all this is in the standard namespace. So three different ways on screen right now. So here I'm declaring a pointer. The type is going to be std unique pointer. Again, it's templated. In this case, a pointer to a magic box that can hold a string. So there's my type right there, std : unique pointer bracket magic box bracket std string bracket bracket. That's the type. I'm naming this pointer my magic pointer. And of course, pointers, these pointer objects, right, they're C++ objects, have constructors. So here I'm calling a non-default constructor, and I'm passing in an object on the free store, right, an actual raw pointer that the unique pointer is going to manage from now on. And so I might as well, I suppose I could have had a raw pointer before this, but to avoid ever seeing raw pointers, I'm going to put the call to the new operator in the parentheses here, in the constructor call. So right here is my call to make a new magic box for strings on the free store. Of course, that returns a raw pointer. That's the input to this constructor call. And from now on, that my magic pointer is going to control access to the object that you just made there with the new operator over on the free store. So that's one way you could do it. That's the only way you could do it when unique pointers were first invented. Now, as of C++ 14, if you're using that compiler set, they didn't want to see new anymore. So they felt that it was a weakness, among other issues, that you were still using the new operator and actually producing a raw pointer at this point in the constructor call. So they said, let's not even see that anymore. And now what you have is you just have a global function called makeUnique. And what you're doing here is you're calling the makeUnique function. You're passing in a type. You're passing in a template type. In this example here, you're seeing a toy box to hold strings. And then the makeUnique function uses new and accesses the dynamic memory and makes a new object on the free store, and it takes control of every part of that process, and now you never see new, and you never actually see a raw pointer whatsoever. That makeUnique function returns, right? The type would actually be the same as what you see up above. It actually returns a thing of type unique pointer type, in this case, toy box type string. So you're going to store that in this my toy pointer. So two options for the type of that. this second line, the type could have been unique pointer bracket, toy box bracket, string bracket, bracket. But of course, on this line, you would have written that twice. So here's a case where you might as well use auto. And it will just look at the thing that you made on the right-hand side of the equal sign, and it can deduce that that must be the type of my toy pointer. Great. You can also create a unique pointer that doesn't have anything yet, and then assign it to an object later on. So here we are making a unique pointer that points to a magic box that holds a string, and we're calling this my fancy pointer. Now, in this case, you can't use auto because you're not initializing it on this line. There's no equal sign with anything on the right, so there's nothing for the compiler to look at to deduce the type that you want. So if you are doing this and not initializing it initially, then you definitely have to specify the exact type that you want. So 3 different ways of doing that. So again, currently, like just the day that I'm recording this, my students would be using C++11, and they will have to continue doing the first option here. Current recommendation in the C++ community is that if you are using C++14 or later, then you want to do it the second way. Use the function and just get all of the news out of your program. So if that is available, use that make unique function. That is currently preferred. Okay, so here is a function that does something with pointers and plain boxes, the change box item function. So a function that encapsulates everything you need to do when you're changing the item in one of these boxes. So what we're going to do here is 2 parameters. The first parameter, as you see, there is a unique pointer aimed at a plain box that holds strings called the box. Remember, you can't use auto there. Cannot use auto currently for function parameters. You have to be explicit about it. And the second thing is a string that's the item that you want to put in that box. So in comes a unique pointer. And remember, normally the way that works is that's passing the pointer by value. So if you were using some other kind of system, at this moment, there would be 2 of the pointers running around, the one in the calling environment that you handed in, and the one that got copied in here. But what happens with unique pointers is, again, there can only be one. So the calling environment must have used the move function call when it got to this point. So it must have called move, handed off the unique pointer into this function. Now the box is the only one in the entire system. And then you're using the box, set item, put the item in it. Okay, so it does whatever work you need. And then in this particular case, we're returning the box, that unique pointer, and then somebody can use that on the other side of the function call. And for what it's worth, when the system does that, it automatically uses the move function. And then once again, the outside recipient of that is the only unique pointer in the universe. So obviously, when this function finishes up, the box goes out of scope, it gets scrubbed off the stack, and then the external version of it that you passed out is, again, the only one in the entire system that refers to that object. So a lot of things kind of happening automatically here. When you're using a unique pointer, there's definitely only one. And if you try to write some code that has more than one, the compiler will complain about that and not allow it. The other thing that you're seeing here is you're using auto here to abbreviate the return type. And when the compiler sees that, it says, okay, I'm just going to look down at the end of your function. You're returning the box. Okay, well, I know that the box is of type unique pointer for a plain box for a string, and I'm just going to fill that in place of the auto. Now, remember what we said on the prior couple of slides is that capacity is a new feature as of C++14. So if you try to use this slice of code in C++11, you got to get the auto out of there, and you do actually have to fill in the full unique pointer, angle bracket, plain box, angle bracket, string bracket, bracket. Okay, and also remember again, what we've said before is you're never going to use a delete statement on smart pointers. It's going to keep track of it, and if all the unique pointers go out of scope, the pointers themselves just handle the deletion, and you never have to worry about that again. So that's kind of nice. Okay, that's what unique pointers look like. So fairly simple idea. There's only one of them. There's no aliases in the world. So that particular cause of dangling pointers is impossible. Great. But again, fairly simple, and that doesn't work for everything in the world. So let's think about the next thing. Shared pointers. Okay, so shared pointers provide a safe mechanism for aliases to implement shared object ownership in the cases where you need that to happen. So the shared pointer, again, is an object between you and the actual free store. And that object, in addition to holding a pointer for real, is also holding a count of how many aliases there are to that object. So as you create new shared pointers referencing a particular object, that count goes up. And then as those pointers go out of scope because they were on the stack, or anytime you set them to null pointer, right? You're never going to use delete, but what you can do is you can just set one of those pointers to null pointer, and the shared pointer reduces the count. It says, okay, that's not referring to me anymore, reduces the count. And then when that reference count clicks down to 0, that's when the shared pointer calls the destructor on the managed object and hands that memory back to the operating system. So that's the idea there. Here's a picture of that. Okay, so using shared pointers, you've dynamically allocated an object on the free store on the heap. And in this particular case, when you're using shared pointers, now you have this middleman manager object that actually is hanging onto the raw pointer, which you're never going to see anymore, and also a reference count for how many of these shared pointers are linking through to that object. So you might have 1 or 2 or 3. That's perfectly fine. And again, this is going to prevent the problem of having aliases that are dangling pointers that are hanging on to addresses that aren't valid anymore. So I've made 3 of these things, and then as they go out of scope or I set them to null pointer, that reference count clicks down to 0. And when the manager object sees that, it calls the destructor on the object, and like we said, hands it back to Windows or whatever your operating system is. Okay, so let's say you want to do that. That seems important. So here is a couple ways you could do that. You could declare one of these objects. So the first way, we have a completely explicit type. You're making a shared pointer to point at a magic box that holds a string. That's the type. I'm calling that particular pointer my magic pointer, great. And I'm initializing it using the global function makeShared, right? Which is the equivalent of the makeUnique that we saw 2 slides ago. So call the makeShared constructor here and tell it what type you want, right? I want a magic box that holds a string, and that dynamically allocates one of those things on the free store, okay? Sets up the shared pointer object, sets the reference count to 1, and then you're going to be using that from then on like it's the pointer. Now, again, there's a case where this is getting kind of long, the type's kind of getting long. You've now, in that one statement, you have said magic box holding a string twice. So this is a case where you could possibly use auto, just fill in auto, and then the compiler will look on the right-hand side of the equal sign, figure out what type you're dealing with, and then basically change the auto into that type. A shared pointer for a magic box holding a string, that's the thing that gets returned here from the makeShared function. So yeah, okay, so you're going to see more of these autos. That kind of makes sense here, obviously. Okay, so you've made a shared pointer. So now let's walk through an example that demonstrates a moment where you need multiple aliases to an object, a case where unique pointer would not work and you really need one of these shared pointers. So we're going to look at an example that we've seen earlier in this course, in our data structures course, when we were building the linked list class. And of course, a linked list is based on pointers, right? You're making individual nodes for each individual data element, and the nodes themselves are chained together with pointers. So the next, and that one has data and a pointer, and the next one has a data and a pointer to the next one, et cetera, et cetera. So previously in our course, we did construct the nodes and the linked list with raw pointers, which is what I'm personally, habituated with. That's what I grew up with myself. But we're going to take that node class and that linked list class and replace the pointers with smart pointers, which are hopefully a little bit safer here. So first of all, we can go back to the node class and make a couple adjustments to it. So you take the node class And you can see here that, as usual, the node class has two pieces of data. Number one, there's the item, whatever you're holding there, and this is, of course, templated. And number two is the pointer to the next node in the chain. And previously, we wrote that as item type star for an item type pointer using a raw pointer. But what might be a little bit smarter now is to make that a shared pointer to a node of item type. I misspoke a little bit. So previously that was a node of item type star, node of item type pointer. So now it's going to be a shared pointer to a node of item type is what we got there. So there's the shared pointer taking the place of the raw pointer right there. Great. Okay, what else needs to change? So the functions in the node class that previously referred to raw pointers, they just become shared pointers. So we have our third constructor here that takes the item type and also a pointer to what's supposed to be the next item in your chain and fills in both of those data members there. So obviously that becomes a shared pointer. And then the mutator to change the next thing in the list, that's also going to be a shared pointer. So basically any place that used to be, let me be careful about this, that used to be a node of item type pointer now becomes a shared pointer for a node of item type. Okay, I think I got that right. Anyway, it's mostly just a copy paste operation of that. So there's that. That's kind of maybe obvious. So now we can go to the linked list class. Here's our linked list class. And specifically, we're going to look at one of the functions that we wrote for linked list, like the insert function, where you take one new piece of data and you specify a particular index for what position you want to put it in. So going to have that same, this doesn't change here, that the function header doesn't change actually. We're figuring out, confirming that you can put a new piece of data in the specified position. Okay, if that's the case. So remember what you got to do there is to find that position, you have to traverse the list, right? And this is the story for all those functions that need to traverse the list. This is a place where you need a shared pointer because you already have pointers actually chaining the list together, but now you need to make another pointer that figures out which node you need to add it after, right? So you're going to have two pointers to the same objects at this point. So here we are to insert it. We are making a new node pointer, and we are calling that make shared function, right? And saying, hey, I need a new node of item type, and I need it to be holding this new entry data. So the make shared calls the constructor for that, calls the node of item type. You get a new node on the free store. It sticks the new entry into it. And then you get the shared pointer address and you put it in new node pointer. Now, again, we're using auto there because the compiler can look over here and say, oh, the make shared function in this case is going to return a shared pointer of type node item type. So that must be the type you want for new node pointer. And it just does that automatically. Great. So it shortens that up a little bit. And now you have the if-else statement to figure out where it goes. If new position is 1, right, if that needs to be the start of your list, let's see what that does here. So what's currently the head pointer is going to be right after the pointer that you just made. Notice that our syntax here looks just like a normal pointer, right? So these couple lines here aren't changing at all, actually. So new node pointer arrow, call the set next function to that, pass in head pointer, and this new node that you just made is now linked to what used to be the first one, right? We're the first one now, and what was the first one comes right after us. Simple. And then the head pointer of the whole list, we're going to set to us, set to our current new node pointer. So that line there is very interesting because new node pointer is holding a reference to our object, and now head pointer has a copy of that reference. So that line right there made two pointers both referencing the one object. So if we'd attempted to do that line right there with a unique pointer, the compiler wouldn't permit it. This is a place right here. If we do this particular algorithm, we need a shared pointer because right at that moment, there's two references of the one object. Now, when this function wraps up, obviously, the new node pointer is local on the stack. That's going to get scrubbed out of the system. And at that point, only head pointer will be holding that reference. So right the second the reference count is 2, when this function wraps up, the reference count ticks down to 1, and only head pointer will be managing that particular object. So what's happening here is you're handing off responsibility, right? We created the new object using new node pointer as our handle. And this line right here is effectively handing off responsibility for the rest of the lifespan of the object over to head pointer. That's what's going to be responsible for it from now on. And new node pointer is about to go away, and obviously head pointer now has to take responsibility for it. So that's exactly the kind of situation where you need a shared pointer for when you hand off responsibility with an assignment statement like that. Okay, so that's kind of the key part. Now, there's an else statement that if the new node goes anywhere else in the chain, you have to traverse it. So here we're calling that getNodeAt function. That actually does the traversal. And if you think about how that worked, inside getNodeAt, there's another pointer. There's another pointer that does the traversal job. So within getNodeAt, the reference count goes up to 2 when it does the traversal. And you can look back at that code when that did that. You get out and getNodeAt, well, that particular traveler pointer goes away, and now the reference count is just 1. You find the correct node that you have to stick your node after, right? And that gets stored in previous pointer. And again, they're using auto for the type there. And then once you find that type, exact same code that we saw before, our node that we just created gets that pointer that used to be before us, which is now going to be after us, if I'm thinking about that right. So just the same call to set next, and then the previous pointer, what we're identifying as the previous pointer, we set our address into that, so the previous thing is correctly chained to us, and then we are chained to what used to be after that thing. So again, this line right here, right at the last thing in that else block, at that very moment, again, there's 2 references, right? There's the new node pointer that we made here, and then there's a copy of it that's stored in the previous pointer node. So right this second, again, there's 2 of them. Same story as the other branch. New node pointer is about to go away, and the reference count will just be 1. And from now on, it will be the pointer inside the previous pointer node that has responsibility for it from then on. And when that finally goes away, right, and the reference count hits 0, then the system automatically calls the delete effectively. So not very many changes we made there. I think all we really did there is just change the type of the new node pointer. The rest of the code is actually identical. But if you think about it closely, there are moments here where there's at least 2, if not more, references to it. And that's very common. Every time we ever did a traversal type operation in our linked list, that was happening. So we need shared pointers. Okay, third thing here. Not going to take too long. So there is a third option called weak pointers. And a weak pointer references an object but doesn't take any responsibility for the ownership of it, right? That's what the shared pointers are supposed to do. So a weak pointer lets you observe an object that exists but doesn't get tangled up in the reference count at all. So with a weak pointer, you accept that fact. You accept that somebody else can make it go away, and the weak pointer has no control over that. So the weak pointer can't affect the lifetime of a managed object. That's what the shared pointers are for. It does not affect the reference count of the managed object. So you can look at it, but the managed object, the managed counter object doesn't recognize the weak pointer as something that has control there. It has a method that you can change it to a shared pointer. So there is a method on these kinds of objects that if you decide differently and need to change it so it's like a shared pointer, you can do that. And it does have another method to test whether the object you're looking at still exists. And that's critical because that solves the problem of the aliases, right? If we were using a raw pointer and we had aliases and one of them deletes it, so it goes away, the second raw pointer has no way of determining that, has no way of figuring out, has the object that I'm addressing gone away? You're just hosed on that. But here with weak pointers, there is a method to check in on that. It's like, has the object gone away? Well, then I'm going to avoid looking at it. So that right there is a key feature that something you cannot do with raw pointers. And again, that's the safety. So if you're using a weak pointer, you have to commit to checking that the object still exists if there's any question about it at all. But that test for safety isn't even possible with a raw pointer alias. So that's pretty important. Okay, so again, just to emphasize that, a weak pointer only observes the managed object. It doesn't have ownership of it. You can't use it to delete or anything like that. It doesn't affect the lifetime at all. So as a little example here, I'm going to make 5 pointers here, I believe, 5. So first of all, we make a shared pointer, right, using the make shared function call, make a shared pointer to a magic box holding a string. We're going to call that shared pointer 1. And then we can make shared pointer 2 and just initialize it to shared pointer 1. Okay, so you have an alias of that object that you just made. And we can make shared pointer 3 and initialize it to the first thing. That's perfectly fine. So you have shared pointer 1 and 2 and 3 that are all pointing at the same object. So your reference count is 3. And then here's an example of us declaring one of these weak pointers. So declaring a thing of type weak pointer for a magic box holding a string. We're going to call that weak pointer 1. And it works to use the initializer to shared pointer 1. Okay, so that kind of initializer with an equals does work for this. And it gets effectively a copy of that pointer. And then you can also make another new weak pointer and initialize it to the first one. So again, using auto here, it looks on the right. It's, well, weak pointer 1 is a thing of type weak pointer for a magic box for a string. So clearly that must be the type that you want for weak pointer 2. So at this point, you actually have 5 different types of pointers referencing to this object. But as far as the reference count goes, it only pays attention to the shared pointers. It just ignores the weak pointers. And the reference count will be 3 here. So here's kind of the layout. So you've only made one object on the free store when you called make shared, right? That's the function that actually made the object. That set up this manager object that's actually got the real pointer into the free store because that's the real deal, but you're not going to see that anymore in your code. And currently the reference count is 3, and it keeps a separate count of how many weak references you have, how many weak pointers. So the weak pointers can persist or not. It doesn't kind of care about that. They might go out of scope in a function or not. But the only thing that really cares as far as the lifespan of the object are these shared pointers. So this object here is going to persist in the free store as long as you have any of these shared pointers around. But again, if you start setting them to null pointer or just going out of scope in a function, or they're a member of an object that itself gets deleted, those things go away. When the reference count hits 0, then it's going to delete the object. And if you have weak pointers around, then it's your responsibility to test with their methods and see if the object still exists before you try to access it or use it. And here's an example of a place where you'd want to use a weak pointer. So let's say you're making a doubly linked list, right? A linked list where the nodes don't just point to the thing after it, but also the thing before it. And that makes it easier to go forwards or backwards in the list. And that actually cleans up some of our traversal code because you can always automatically find the thing both before and after it. So if that's what you want, you would make a node class here we're calling double node, that contains one piece of data and then 2 pointers. And previously, the 2 pointers would obviously be raw pointers for us. Now, in this case, what we're doing is the private data is one item of some generic type. And what we're doing is that we're making the normal pointer, the one that goes to the next one, we're making that a shared pointer to whatever type of node you're dealing with, because that's the one that's going to be responsible for managing and deleting it when you need to. The other pointer, the one that goes forwards in the list that normally isn't there in a normal list, we're going to make that a weak pointer because that one can get you to the previous node. You can find out what it is, but we don't want that one to be responsible for maintaining the node's data on the free store in memory. And if we didn't do that, if we didn't restrict ownership to one instead of the other, we'd have a problem when we try to clear out the linked list. Because what would happen is that you would delete a particular node and that particular pointer would go away, but you'd still have the pointer in the node, right? So you try to delete a node, but you still have a pointer in the one before that, and so the node you tried to delete actually winds up persisting because all you did was reduce the reference count from 2 down to 1, and then the thing still sticks around for a while, which is not what you want. So it's easier here to make one of the pointers the shared pointer, and then you can delete the node, and it says, yeah, the reference count is 0, and then the node actually goes away out of the free store. So doing this is indicating that one specific pointer, and we know which one it is, it's the next pointer, is actually managing the object. And so that makes it a little bit easier to add new things and delete them when we need to. So that's a good example of a place where you would want a weak pointer. You know, one is responsible for it, and the other one is just looking at them. Not the same thing. Okay. So there's the story of smart pointers in C++. And we have the unique pointers, probably the simplest one there, that just makes it impossible to run into the alias problem with dangling pointers. These kinds of examples with linked lists, or we could come up with lots of other examples, mean that you need aliases sometimes, so that's what the shared pointer is for. And then this example here is sometimes you can use a weak pointer when you don't want to get involved with it making the object more persistent. So 3 different options in that toolkit there. Now remember that if you were a longtime C++ programmer like me, you might have been using an auto pointer years ago, which is basically trying to be a unique pointer but didn't quite do the job properly. Now we have these 3 options. Maybe in the future there will be more options. Maybe they will continue to evolve possibly. At this point in our course, we'll probably start restricting ourselves to these smart pointers going forward. And remember that professional programmers, professional software engineers, the inventor of C++, Mr. Strustrup nowadays, would say for professional release grade quality code, you don't want to see raw pointers anymore. You shouldn't see raw pointers. We don't want to see new. We don't want to see delete. We just want all that stuff to be handled automatically by the smart pointers. So going forward, we'll probably proceed in that direction from now on, and maybe for the rest of our course here, we'll exclusively use smart pointers. Now remember at this point, we've seen 2 different versions of the linked list, right? We've seen the node in linked list that use raw pointers in our course, and then now we've also seen a variant that uses smart pointers instead. So hypothetically, you know, nothing changes as far as behavior to an outside programmer. So you could take a program that uses a linked list and just swap one of those in for the other, and the client programmer working the application might not ever even know the difference that happened. Hopefully, the external behavior is the same all the time, but we're just protecting ourselves a little bit more in case we screw up our linked list code or something like that. And I'm also glad that we did spend time learning about what I might want to call real pointers, raw pointers. And we do know that that's how computers actually work, how CPUs really manage memory with just numerical addresses that we call pointers, and that's how the CPU works. And I'm glad that we can interface with our computer architecture and our assembly language class, again, where that's the only thing that exists, because smart pointers is certainly an element of a high-level language like C++ and don't exist at these lower-level languages. So I'm glad that we know the real story, and you know, we wouldn't have even been able to explain what manager objects do, like on the prior slide, because they hold an actual real raw pointer. So if you understand the job that's happening about how they're keeping track of the object in the free store, that explanation boils down to actual pointers. But going forward, we should probably use these smart pointers to protect ourselves. Okay, that makes sense. We'll see that in the future. Now, when we come back next time for Interlude 5, we're going to dig back into more about class inheritance and polymorphism. That is so important. So we ought to take a little bit more attention about exactly what that's doing for us, and we'll provide some details. If you ever wondered about how polymorphism actually literally works on the CPU like we're talking about, we'll give some additional details next time on that when we look more about class relationships and ways that you can reuse classes intelligently. So I hope you'll join me for that, and I'll see you then.